types of radioactivity. So Curie was looking at finding different radioactive elements. Ernest Rutherford and others were looking at what exactly is this radioactivity? What is this stuff that's coming off? So they found that the nuclei of radioactive elements are unstable, they spontaneously decompose, and they're falling apart. Little pieces just fly off. And there are several different types. We're going to talk about 4 of them: alpha rays, beta rays, gamma rays, and positrons. So first we need to review nuclear symbols. We learned this earlier, but you may have forgotten it. So this is a nuclear symbol. The X is representing the chemical symbol. The A is representing the mass number. The mass number is the number of protons and neutrons that are found in the nucleus of that atom. And down below is the atomic number, and that's the number of protons. Because different isotopes will have different numbers of neutrons. Okay. Most elements have different isotopes. When we're talking about a particular isotope, we call it a nuclide. So we'll be using that word, nuclide. That just means a specific isotope of an element. We can represent them by their nuclear symbol or by the element name or symbol followed by the mass number. So we could say carbon-14 or C14. And then we also have symbols for the main subatomic particles. There's a proton, the symbol's P. It has 1 proton and 1 proton. A neutron is N, and the mass number is 1. That's the sum of the protons plus the neutrons. The number of protons it has is 0. And then we have an electron, and the electron is E. It has no protons or neutrons, and this may become clear later. Just deal with it. It's a -1. That's confusing to students. Okay, alpha decay. So an alpha particle gets spit out. An alpha particle has this symbol because it is a helium nucleus. It's identical to a helium nucleus. So helium 4, it's got 2 neutrons, 2 protons, and here's the 2 protons. Identical to a helium nucleus. So here we have a nucleus, and it undergoes alpha decay, and a little piece of it comes off, an alpha particle. 2 protons, 2 neutrons stuck together, and they go shooting off into space. I know, it's crazy. We represent this happening with nuclear equations. In a nuclear equation, the sum of the atomic numbers on both sides of the equation has to be equal. The number of protons and neutrons on the reactant side and on the product side has to be equal. The sum of the mass numbers must also be equal. So here we have an example. Here we have uranium-238. It's got 92 protons, and the mass number is 238. When it undergoes alpha decay, it spits out an alpha particle. And this is what's left. So the mass number, 238, lost 4. So the mass number of this daughter nuclide must be 234, because 234 plus 4 has to equal 238. And it lost 2 protons, so the atomic number went down also. Went from 92 to 90. Now, why did the symbol change? What's element 90 on the periodic table? Thorium. In nuclear reactions, the elements do change. Okay, we said earlier, in chemical reactions, that atoms are neither created nor destroyed. This is the exception. This isn't a chemical reaction, this is a nuclear reaction. You can turn one element into another. The alchemists were obsessed with turning things like lead into gold. Can you do it? Yes. Is it cost effective? No way. There's no point in doing it. But can it be done? Yes, you can make things into gold. So how do we figure this out? So here's thorium, thorium-232. It emits an alpha particle. And then we have to figure out what does it make? So what's left after this comes off? We take this 4 and we subtract it from the 232. So x here must be 228. Because 228 plus 4 will equal the 232. The mass numbers on each side have to be equal. And the atomic numbers have to be equal. Here's 90. It lost 2. That means there's 88 left here. Radium is number 88. It turned into radium. So this is radium. It has an atomic number of 88 and a mass number of 228. And that's what goes in there. It's really simple math with whole numbers, just adding and subtracting. Should be, kind of refreshing after some of the stuff we've done. Let's write the nuclear equation for the alpha decay of polonium-216. So polonium-216, PO, 216 is the mass number. The mass number is always given because there's no other way to know what it is. The atomic number isn't given here because we can figure it out from the periodic table. Looks like it's 84. You do not need to know the names of some of these crazy elements. You can just find PO on the periodic table. What's the big number above it? It's 84. So we've got that. And this is going to give off an alpha particle. This is always an alpha particle. And so that's something you have to memorize. That's the alpha particle. So it's going to give that off. And now we're going to try to find out, well, what goes in here? Well, 216 minus 4 would be 212. And 84 minus 2 would be 82. And then we look on the periodic table and find the symbol for 82, which is lead. So we write that in here. And that's all there is to it.
And the alpha particle is always helium?
This is always an alpha particle. So that's the hardest part. Remember, well, what the heck is an alpha particle? Because I'm also going to tell you about a beta particle and a positron. There's going to be 3 of them. But this is the alpha particle.
Depending on which one they give you, that's what's going to be.
I know to write this because it says alpha decay. All right? So we use an analogy with motor vehicles to help us understand some characteristics of the different types of radiation. Alpha radiation is like a semi-truck, an 18-wheeler. It is big, it's massive compared to the other forms of radiation. It has the highest ionizing power. Ionizing power is the ability of radiation to ionize other molecules or atoms. In living organisms, having your molecules ionized can cause a lot of problems because that changes the chemical reactions that they undergo. So you don't want your molecules being ionized. And that's a primary mechanism by which radiation damages and kills living organisms. So this is the Mack truck of radiation. High ionizing power, just, man, slam bang. But it has the lowest penetrating power. So penetrating power, we're thinking about a traffic jam, like New York City traffic jam. You get a semi in city traffic. Is it hard to get through? Mm-hmm. Yeah. I was in 2 traffic jams in Reedley this morning. There's some big sewage problem, so there's a couple of places blocked off, and then there was another place where they decided to do some work on the side of the road and narrowed it. I'm like, awesome. Doesn't happen much. But here in Fresno, you see it, especially on the freeways. Big jam of traffic. That truck has a hard time getting through. So it has the lowest penetrating power. Penetrating power is the ability of radiation to penetrate matter. In order for the radiation to ionize molecules and atoms, it has to get into the cell. Well, alpha radiation is not very good at getting into the tissue. It can't get through. because of its large size. It can be stopped by something as simple as a sheet of paper, by a t-shirt, even by a layer of air is enough to stop it. Once it gets in, though, it's really, really dangerous. So if you inhale alpha particles or ingest alpha particles, now they're inside you and they're going to be more dangerous. Beta decay. So the beta particle has this symbol. That is an electron. How does a nucleus emit an electron? Does that bother anybody? Are there electrons in the nucleus? No. Well, it turns out that you can take a neutron apart into a proton and an electron. So what happens is a neutron turns into a proton and an electron gets kicked out. And that's why this has a -1, because we've lost. So here we have radium, and when it undergoes beta decay, we get the mass number is the same, but the atomic number goes up because a neutron turned into a proton. The neutron's lost, we've gained a proton. And the mass number only counts protons. I'm sorry, atomic number counts protons. The mass number is the same because the sum of protons and neutrons is still the same. Here we have an illustration. This neutron becomes a proton and an electron gets spit out. So let's write a nuclear equation for the beta decay of actinium-228. So AC-228. Need the periodic table to figure out what its atomic number is. 89. Beta decay. So that's an electron. I write this because it says beta decay. And now I'm just going to look at the mass number and the atomic number and make them add up to the same thing on each side. So 228, I need 228 here to add with 0. So that stays the same. Here I've got 89. Over here I need 90. 90 and -1 will equal 89. So 90 is thorium. Okay. Like I said, the hardest part is remembering what's the symbol for a beta particle. No. We'll not give that to you. They won't. So beta radiation is like a 4-door sedan. Lincoln Town Car or something. Less massive than the alpha particle. If it runs into you, it's not going to do as much damage as the big truck. So the ionizing power is less. But it has higher penetrating power. A car is able to get through a traffic jam more easily than an 18-wheeler, right? So it has greater penetrating power. So piece of paper, thin t-shirt, not going to stop this. But a sheet of metal or a thick piece of wood could stop it. So this is more dangerous outside the body than the alpha because it can get through your cell walls and stuff much more easily. But it's less damaging if ingested than the alpha particles because its ionizing power isn't as great. How would you ingest it? Well, like if you were a really sloppy scientist and you were working with radiation and you had a donut on the bench top, you could ingest it. It's not something that happens a lot. Third type is gamma radiation. This is a Greek letter gamma. This is actually electromagnetic radiation, not particles. So it's not a particle. They're called gamma rays because they aren't particles. So they're really just high energy photons. If you remember back to the electromagnetic spectrum, way at the high energy end was gamma rays, above X-rays. So it has no charge, no mass, and so the element doesn't change. It's still the same element. We usually see gamma rays being emitted with other types of radiation. So here's the symbol, and it's a wave. It's not a particle, so there's no picture for it. So here's an example, uranium-238 undergoing what kind of emission? Alpha to thorium, also giving off gamma. Okay, there's no way to know just from, if I asked you to write the alpha decay equation for uranium-238, I would not expect you to know to stick gamma ray in there. But it often accompanies other things, so we're not going to write equations for it. Gamma rays are the motorbikes of radioactivity. So traffic jam. If you're on a motorcycle, stalled cars, stopped traffic, you can weave between and get in. Gamma rays have very high penetrating power, but the impact is less, and so low ionizing power. To stop gamma rays, it takes several inches of lead or thick slabs of concrete. So, the big bunker, the thick walls of concrete, that's going to stop gamma rays. Fourth type is a positron. So a positron is the antiparticle of the electron. It's like the opposite of an electron. So it's got the same mass, but it has the opposite charge. So its symbol, it has 0 for the mass number, but +1. It's the opposite of beta. So electron, positron. This is a positive electron, basically. If you get the positron colliding with an electron, those two particles annihilate each other. It's like, the science fiction matter, antimatter. Poof, they cancel each other out, right? So what happens is the positron and the electron will annihilate each other, and the tiny bit of mass that they did have is converted into large quantities of energy in the form of gamma rays. So a proton, in positron emission, a proton gets converted into a neutron and a positron. So the proton becomes a neutron and a positron. So when we write the equations, we really just need to know this symbol. So the atomic number decreases by 1, but the mass number stays the same. And the positrons are similar to the beta particles in terms of ionizing power and penetrating power. All that's different about them is their charge. So there's a table from your textbook giving a summary of the 4 different types. So let's write an equation for positron emission. Sodium, 22. So sodium is Na. Mass number is 22. We look at the periodic table. Atomic number is 11. Positron emission, we've got E0 plus 1. So we need to find the mass number here. What plus 0 equals 22? 22. And what plus 1 equals 11? 10. Then we go to the periodic table. Neon is element number 10. So by positron emission, sodium 22 becomes neon 22. Yes?
So would gamma also be a part of this, or just finish up?
Ooh, and I forgot the plus. There could be gamma emission with this. There could be, yeah. But there doesn't necessarily have to be. Any questions?